sled. We're given the mass of the sled. It is a 10 kilogram sled. We should put that up here.
I saw it in the video just saying.
Okay.
Yeah.
Okay, and we have an initial velocity of 2.2 meters per second. And we're keeping in mind that the net work is equal to the net force times the displacement times the cosine of the angle. And net work is also the change, equal to the change in kinetic energy. So let's work with that kinetic energy thing first, because what we want to know is how far this sled moves before it comes to a stop. Okay? Well, at the point when it comes to a stop, what's its VF? 0. So what's its kinetic energy? 0. So if we look at the delta KE, that's 1/2 mass VI, or VF squared minus 1/2 mass VI squared. Okay. So the change in kinetic energy, this is all 0, is equal to negative 1/2 mass VI squared. That seems like it'll be useful. So we'll tuck that away. So everybody's okay with how we got that?
Yes.
Okay.
Okay.
I got it. There's just a glaring point.
Oh, okay. Sorry. Now, what is doing work on the sled? So you gave it a kick. You set it in motion. Once your foot leaves the sled, are you doing any work on it?
No.
No. What is doing work on it? Friction. The friction between the sled runners and the ice is slowing it down, and therefore that's doing work on it. So now let's look at the work done on the sled. So the net force on it, the only force on it once it leaves your foot is what? Force of friction. Well, we're not given the force of friction. What are we given? We're given the coefficient of friction. What else are we given? The mass of the sled, and there's no force on the y-axis that changes normal. So let's do a little side work over here. Mu k equals what?
0.1 F.
No. Mu k equals equations.
Oh.
Mu k equals Fk over Fn. If we draw our sled here, we can prove to ourselves that Fn equals Fg. So this equals Fk over Fg. And we'll get rid of this. So we can rearrange that to say that mu k times Fg equals Fk. And what's Fg equal to? Mass gravity. So mu k mg equals Fk. Well, lo and behold, that can be plugged in there. Okay, so let's bring this down. So now we have the network is equal to
2 days now and you just got it.
mu k mg times delta x. So at this point, we have mu k, we have mass, we have gravity. This is what we want, but we don't have the net work, except we do. Because guess what? Net work is equal to the change in kinetic energy. The change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy. The final kinetic energy was 0. So that is equal to the net work. It's okay. Your head will stop hurting soon. Once the numbness sets in. So now we have mu k mg delta x equals negative 1/2 m vi squared. Okay. It's going to be beautiful.
I have a question. What
Yes.
about cosine theta?
Oh, I'm sorry. Sorry about that.
Oh, just made it worse. Do we need it for this?
Well, we don't, but we want to make sure we acknowledge that we don't. So yeah, we don't need it, but we want to make sure we clarify because there may be cases where we do. Okay, let's bring all this up here so we can see it clearly.
Wait, wouldn't that be -1/2 MV?
Yeah, that's what I was
It is,
thinking.
sorry.
Oh, and you gotta
All right,
then
you
you
can
count
count
the X.
mg delta x cosine theta equals -1/2 mvi squared. It just looks ugly. It's not really that hard. We'll get rid of this so we have some room to work.
It's -1/2, correct?
Yeah, sorry. There we go. Okay, now let's look at the angle between the force that's doing the work and the displacement. What is it?
0. Or 180.
It's 180. What's the cosine of 180? Go ahead, do it for yourself real quick. 180. Oops, clear. Cosine 180. -1. So what we're saying there is that we've got an opposition of direction. We're saying that the force is acting in one direction, the displacement is in the other direction. Okay? All right, so we can start plugging stuff in. So mu k is 0.1. Yes? Oh, we got to rearrange. Sorry. Jesus, Pizzo. As I said. So this is what we want. Well, if we do this, delta x equals negative mvi squared over 2 mu k mg cosine theta. I did it all in one step, but I think you can all handle that level of algebra. Okay, now we're rearranged. Now we can go ahead and start plugging in numbers. So, the negative of mass, which was 10.0 kg, velocity squared, 2.2 meters per second squared, all over 2 times 0.1. What are the units from UK? There are none. Good. Times mass, 10.0 kg, times gravity, 9.81 meters per second squared, times cosine of 180. Hoi! And we could get rid of that 10 kg. That would be perfectly legal, and just leave that as a -1. Okay, so
We just know that mu k is 0.1.
pardon?
We just know that mu
Like
k
they
is
can-
0.1. Or is-
It was given in the problem. Sorry. Yeah, I should list it over here. Okay, so 2.2 squared times -1 divided by the quantity. 2 times 0.1 times 9.81 times cosine 180. Okay. What'd you get? What'd you get? What'd you get? We get a different number than the book because, of course, their sig figs and rounding are terrible, and I'm sure that they rounded numbers to put into that. So yeah, I get a delta x of 2.46687054 meters. Are those units correct? Let's check. So that was meters squared. Second squared goes away. Meters squared divided by meters is meters. So, with sig figs, we have what, 2 sig figs? So delta x, we would say is 2.5 meters. The book says 2.4, but they're wrong. So, Gesundheit. Okay, questions on those? These are a little bit more challenging because we're now putting together, we're doing very much the thing we did with net force and mass acceleration, where you're taking 2 things that are equal and setting two things that are separate but equal, and setting them equal to one another to solve for something. So, all of the practice problems on 5C are assigned. There are 5 of them. Page 176. And that's where we'll stop today.
And all of 5 are correct.
All